Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual ferment of the late 17th century, driven by a renewed faith in empirical evidence, found one of its most potent and unexpected agents in the person of a cloth merchant from Delft, Antonie van Leeuwenhoek, armed with single-lens microscopes of his own peerless construction, directed his gaze toward a universe hidden within the familiar. His letters to the Royal Society of London, the primary conduits for his discoveries, document a journey into the foundational structures of the living world. The observations from 1675 concerning the human body represent a particularly concentrated and revolutionary body of work. This essay undertakes a rigorous evaluation of the specific claims, methodical innovations, and conceptual frameworks presented within Leeuwenhoek's 1675 physiological investigations. It will proceed by systematically analyzing the content of these communications, assessing the assertions made about blood, hair, skin, and other tissues, thereby illuminating the precise nature of his contribution to the nascent science of microanatomy and revealing the profound implications of his particulate vision of human substance, sexually in the particulate nature of blood. Leeuwenhoek's correspondence from the autumn of 1675 presents a radical reinterpretation of the body's most vital fluid. His central claim, articulated with the confidence of direct sight, is that blood consists of a vast multitude of discrete, small globules suspended in a clear liquor, or serum. He describes these particles with meticulous detail, noting their generally round shape, though he also perceives them as oval or flattened when they are pressed together or viewed from a different angle. This observation on morphology represents a departure from all prior conceptions of blood as a uniform, homogeneous humour. His methodology was one of elegant simplicity and effectiveness. Using a fine needle, he would draw a minuscule quantity of his own blood, immediately enclosing it within a slender, custom-drawn capillary tube. This technique was a crucial innovation, as it created a sample layer thin enough to be rendered translucent, allowing his microscope's light to pass through and reveal the internal contents. He proceeded with a quantitative impulse that characterizes much of his scientific work, estimating that 100 of these blood globules placed side by side would equal the diameter of a coarse grain of sand. This effort to measure the unseen, to give it scale and dimension, established a new standard for microscopic reporting. His interpretation of these findings was equally mechanical and physiological. He posited that the red colour of blood inhered in the globules themselves, a physical property of the particles, which, when densely packed, produced the familiar sanguine hue. He further connected the constant, rapid circulation of these particles through the finest vessels with the generation of bodily heat and the maintenance of life, proposing a physical basis for a fundamental vital property. The evaluation of these claims reveals a foundational moment in hematology. Leeuwenhoek was providing the first detailed description of red blood cells. His account of their shape, their aggregation in narrow vessels, and their suspension in plasma is remarkably prescient. His implicit dismissal of humoral theory, which explained health and disease through the balance of four fluid essences, in favour of a mechanical, corpuscular system, was a monumental conceptual leap. He transformed blood from a mystical fluid into a complex physical substance, a suspension of functional components whose properties and behaviours could be observed, measured, and explained. Section to the composite architecture of hair in his investigations into the appendages of the human body, Leeuwenhoek turned his lens upon the familiar structure of hair, revealing an unexpected internal complexity. His primary assertion is that a single human hair is a composite object, possessing a distinct internal and external organization. He describes it as comprising an outer layer, which he terms the cortex or bark, and an inner substance, the medulla or pith. This claim directly counters the view of hair as a simple, uniform filament. His method involved both longitudinal and transverse examinations. By slicing thin cross-sections, a delicate and skillful procedure with the tools at his disposal, He could perceive this layered arrangement. He complemented this approach with a comparative analysis, examining the hairs of other animals, such as deer and sheep, to understand which features were general and which were specific. He noted, for example, that the internal pith was more pronounced in certain animal hairs than in his own. This comparative methodology added a layer of sophistication to his analysis, allowing him to form generalizations about the principles of hair construction across different species. His interpretation of these structures was deeply functional. He described the outer surface as being covered in tiny, overlapping scales, a feature that contributed to the texture and interactive properties of hair fibers. He theorized that hair growth was a physiological process rooted in the skin, with a hair shaft being extruded from a follicle. This model of growth, originating from a specific anatomical structure, framed hair as an organized tissue produced by the body, a stark contrast to older ideas of it being a mere excretion or condensation of bodily vapors. Critical evaluation confirms the brilliance of these observations. His description of a cortex and medulla established the basic framework for the science of trichology. His perception of the cuticular scales, though their form was difficult to resolve perfectly with his instrument, was a landmark discovery, explaining the way fibers interlock and feel by providing a detailed microanatomical account. Leeuwenhoek transformed hair from an inert bodily feature into a dynamic, complex biological structure, a product of a specific and continuous physiological manufacturing process within this. Section 3. The lamellar structure of the epidermis. Leeuwenhoek's curiosity extended to the very surface of his own body, leading him to scrutinize the nature of the skin. His major claim regarding the epidermis, derived from examining the scurf or flakes that constantly shed from its surface, is that this outer layer is composed of a multitude of thin, flat, overlapping scales or little plates. He saw his own body as being perpetually covered in these tiny, lifeless components that were the terminal stage of a biological process, the source of his sample material. His classic Leeuwenhoek, he simply collected the mundane detritus of his own existence, demonstrating his conviction that profound truths were accessible in the most commonplace substances. He would mount these delicate, almost transparent flakes and observe them with transmitted light, revealing their polygonal shapes and their arrangement in layered sheets. This simple, direct method yielded an insight of immense significance. His interpretive framework for this observation was one of dynamic renewal. He conceptualized the skin not as a static container but as a constantly regenerating organ. The shedding of these scales was evidence of a continuous upward movement and replacement of skin components, a vision of the body in a state of perpetual material flux. He speculated that the tightly layered arrangement of these scales before they were shed formed a protective barrier, a sort of biological armor that was both tough and flexible. An assessment of this claim shows it to be the first accurate description of the stratum corneum, the outermost layer of the epidermis. Leeuwenhoek's work provided the cellular, or in his terms, scaly, basis for the skin's function as a boundary between the body and the world. It replaced the abstract notion of skin as a simple membrane with a concrete, structural model. It is a moment of intellectual irony that in something as trivial as a skin flake he discerned a principle of ordered, continuous biological regeneration that is fundamental to our understanding of epithelial tissues today. His work made it clear that the body's envelope was as structurally intricate as its internal contents. Section 4. The fibrillar composition of muscle and tendon. Moving deeper into the body's substance, Leeuwenhoek's investigations in this period addressed the machinery of motion, muscle and connective tissue. He asserted that muscle flesh is composed of exceedingly fine, parallel filaments, which he called fleshy fibrils. He further observed that these primary filaments were bundled together into progressively larger fibers, creating a hierarchical structure. In his examination of tendons, he claimed a similar fibrillar construction, describing them as dense bundles of parallel fibers that provided the structural linkage between muscle tissue and bone. His methodology for these observations required careful sample preparation. He likely used thin slices of cooked, or boiled, meat, as the cooking process would help to separate the connective tissues and make the fibers more discernible. He would then meticulously tease these fibers apart with fine needles under his microscope, a painstaking process of manual dissection at a microscopic scale. This allowed him to trace the continuity of the fibers and understand their bundled arrangement. His interpretation was overwhelmingly mechanical and structural. He envisioned the body as a finely wrought machine, and the fibro arrangement of muscle was its essential design principle. The immense number and parallel orientation of these tiny fibrils directly related to the muscle's capacity for generating strong, linear force during contraction. He proposed that the very act of muscular contraction must be the result of some change, perhaps a shortening or coiling, occurring simultaneously within these millions of constituent fibrils. The connection of muscle to bone via the similarly fibred tendon was, in his view, a perfect mechanical solution for transmitting this force. Evaluating these claims confirms their foundational importance for histology and physiology. Leeuwenhoek's description of the hierarchical bundling of muscle fibrils, from myofilaments to fascicles, remains a cornerstone of muscle biology. His work provided the first strong evidence against the prevailing concept of parenchyma, the idea that organs were composed of undifferentiated, amorphous pulp. Instead, he presented a vision of tissues as highly organized, architecturally sophisticated materials, whose microscopic form was perfectly suited to their macroscopic function. He established, through direct observation, the structural basis for the body's biomechanical systems. Section 5. The unifying and erroneous globular hypothesis crosses various physiological investigations of 1675. An overarching conceptual framework begins to emerge from Leeuwenhoek's work. This is his grand hypothesis that all living tissues, at their most fundamental level, are composed of globular or particulate units. Having first seen them definitively in the blood, he began to perceive, or project, a similar globular constitution in other substances. He speculated that flesh, fat, nerve, and even the hard substance of bone might ultimately be resolved into arrangements of these elementary globules, differing only in their size, density, and mode of aggregation. This globulist theory was less a direct observation and more of a unifying philosophical commitment, a product of the prevailing Cartesian and corpuscularian worldview that favoured mechanical explanations for all natural phenomena based on the interaction of particles. Leeuwenhoek's microscope seemed to provide the empirical proof for this philosophy. His method here was one of analogical reasoning, extending a pattern observed in one domain to all others. The interpretation of this framework was powerful and ambitious. It represented one of the first attempts in the history of biology to propose a universal, microscopic unit of structure for all living matter. It sought to explain the diverse properties of tissue's softness of fat, the firmness of muscle, the rigidity of bone as emergent properties arising from the physical characteristics of their constituent globules. This was a profoundly reductionist and modernist project, seeking a simple, common denominator for the bewildering complexity of life. A final evaluation, however, must recognize the limitations of this hypothesis. The universal globulist theory was a magnificent oversimplification. Many of the globules he described in solid tissues were likely optical artifacts created by the spherical and chromatic aberrations of his simple lenses. In other cases, he was seeing actual cells, but his theoretical predisposition led him to interpret their complex three-dimensional forms as simple spheres. There is a certain intellectual elegance, a dry historical humour, in the fact that this profoundly incorrect theory was so intellectually fruitful. By relentlessly seeking a fundamental, repeating unit of life, Leeuwenhoek's globulism primed the scientific imagination for the cell theory, which would finally emerge a century and a half later. His error was in the specifics of the unit, not in the revolutionary idea that such a unit existed. In conclusion, The body of work produced by Antonie van Leeuwenhoek in 1675 constitutes a fundamental turning point in the scientific understanding of the human form. This detailed evaluation of his claims reveals a pattern of groundbreaking empirical discovery coupled with bold, and at times flawed, theoretical synthesis. His section-by-section revelations concerning the substance of the body replaced ancient abstractions with tangible, observable reality. The critical assessment of his claims regarding blood demonstrates his discovery of red blood cells and his mechanical reframing of circulation. The analysis of his work on hair and skin shows his identification of their composite, layered, and regenerative nature, establishing them as complex tissues. His investigation of muscle provided the first clear picture of its hierarchical, fibrillar architecture, laying a foundation for biomechanics. While his overarching globulist hypothesis was an overreach, its underlying search for a universal building block of life was a powerful and necessary step in the progression of biological thought. Leeuwenhoek's methodology, a potent combination of superior instrumentation and ingenious sample handling, unlocked a domain of reality that no one had ever witnessed with such clarity. The consequence of his 1,675 observations was the irrefutable establishment of a microscopic dimension to human anatomy, a vision of the body as an intricate machine built from an immense population of smaller, functional components. His letters from the singular year did more than present new facts. They offered a new way of seeing ourselves, transforming the human body into a landscape of profound and endlessly fascinating structural order.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.